Hi all, this is Dr. K.G. Shanti, Professor, EC Department, R.M.K. College of Engineering and Technology. In this PPT, we are going to study about Unit 3 of Transmission Lines and Waveguides. Unit 3 talks about impedance matching in high frequency lines. How are we going to achieve impedance matching is dealt in Unit 3, where we are going to make use of quarter wave transformer, half wave transformer, single stub and double stub matching. What is meant by impedance matching? Right? Now, if I want the entire signal to be transmitted from the source to the destination, then the one of the important condition is the source and the load are to be matched. We all know maximum power transfer theorem, right? So a part of the transmission lines can be used for the purpose of impedance matching, correct? Right? Impedance matching is done. Why? Because it is used to minimize reflections so that the load impedance is equal to the source impedance. Right. This impedance matching by insertion of section of transmission lines is what is shown here. We have three section of transmission lines can be used. L is equal to lambda by 8 represents 8-way line. L is equal to lambda by 4 represents quarter wave transformer. And L is equal to lambda by 2 represents half wave line. And the other method is going to be making use of single stub and double stub matching. Now let us look into how impedance matching is achieved by using a 8-wave line. And you have to be very clear that impedance matching is nothing but the source impedance and the load impedance are to be matched. Only then maximum power or maximum energy from the source side is transmitted to the load side. Okay, right. Now the input impedance equation of a dissipation less line is given by Zs is equal to R0 into Zr plus Jr R0 tan beta s by R0 plus Jzr tan beta s. I hope you are all very clear with various parameters. R0 is the characteristic impedance, Zr is the load impedance or impedance on the receiving end. We are going to, the Zs represents the input impedance. Okay. Right now, what is beta? Beta is nothing but 2 pi by lambda. Okay. S is nothing but the distance measured from the receiving end. Now, with that, all that in mind, beta s. Now, let us calculate beta s. Beta is 2 pi by lambda. For a quarter wave line, it is lambda by 8. So, lambda gets cancelled. 2 and 8. So, it is pi by 4. Now, what I'm going to do is, instead of tan beta s, I'm going to replace it as tan pi by 4. And you all know what is tan pi by 4? Tan pi by 4 is 1. When I substitute tan pi by 4 is equal to 1, what do I get? Zr plus Jr0 by R0 plus Jzr. Zs is equal to R0 into this value. Right. Now, when I take the magnitudes, right? When I take the magnitude of numerator and denominator, both are going to be equal and they get cancel each other. Right. When I say magnitude, you all know what is meant by magnitude. Magnitude of the numerator is going to be what? It is going to be Zr square, right? It is going to be Zr square plus R0 square, right? In the same way, what is the magnitude of the denominator? Even the magnitude of the denominator is going to be square root of Zr square plus R0 square. So both will get cancelled each other, and so what you will get? You will get Zs is equal to R0. Correct? Right. Now let us see how impedance matching is achieved by means of a quarter wave transformer. A transmission line of length lambda by 4 is called as a quarter wave transformer. Right. Now this is the input impedance equation of a high frequency line. Zs is equal to R0 into Zr plus J R0 tan beta s by R0 plus Jzr tan beta s. where S is the distance measured from the receiving end. Now once again, what should I do? Beta is nothing but 2 pi by lambda. Beta S I have to calculate. S is nothing but lambda by 4. Do the calculations. The input impedance of a line of length lambda by 4, that is S is equal to lambda by 4. We are calculating. Beta S is nothing but 2 pi by lambda into lambda by 4, which is nothing but pi by 2. Correct? Now what happens here now is, what I'm going to do is, let us calculate tan pi by 2. Tan pi by 2 is infinity. Right now, I cannot directly apply tan pi by 2 as infinity here. What I do is divide the numerator and denominator by tan pi by 2. When I divide the numerator and denominator by tan pi by 2, I get zr by tan pi by 2 plus jr naught divided by r naught divided by tan pi by 2 plus j zeta. Now what happens here? Anything divided by infinity. What is anything divided by infinity? Anything divided by infinity becomes 0. Correct? So what am I left out with? Here you have j r naught by j zr, right? J gets cancelled. So what will I have? R naught by zr. Already one R naught here. So R naught into R naught is going to be R naught square by zr. So this is input impedance of a line between, that is when a quarter wave line is used between the source and the load. Okay, right. Now generally this formula is very important, right? Now if I have a source ZS and a load ZR, then, right, now what is the characteristic impedance of the line that I have to join, right? So in that case it is going to be R naught is equal to square root of ZS into ZR. That is what is written here. So what I have, Z naught is equal to R naught is equal to square root of ZS into ZR. So the input impedance of the line is equal to the square of characteristic impedance of the line to that of load impedance. So that is what is shown by this equation, right? A quarter wave transformer transmission line is chosen such that it can match a load of, that is it can match ZS and ZR. That is ZS is the source end impedance. This is the source end impedance and this is the receiving end impedance, where Z0 is equal to R0, which is equal to square root of ZS into ZR. Thank you all.